All right, so welcome back. Of course, you haven't been anywhere, but it's nice to see everyone again. Today we have a very special guest, Greg Meredith.
Hey, how's it going?
Good, it's nice to see you again.
Hey, thanks for having me out here.
Sure, man. Last time you were here, you were jamming with Brian Beckman at the Whiteboard, Monadic, kind of...
Monads and coordinate systems.
Monads and coordinate systems, man.
But it was definitely an improv.
It was an improv.
Big jam.
And people liked it.
Oh, well, way cool.
But it was a little Ornette Coleman for some folks out there. So you're actually doing something incredibly interesting with Monadic web design or design patterns.
Yeah.
And you're going to take us through today, beginning with your definition of a monad so that people like me can understand it.
Yeah, absolutely. Yeah, I got to say, we tried this out before.
Yes, we did.
And it totally tanked. It totally tanked. So this is actually take two.
This is take two. Well, before, in all honesty, it was a lecture.
Yeah.
And you were talking to 3 cameras, which can be a little daunting, and it's not. I mean, and plus,
they just look weird. They look like aliens from outer space,
and they don't ever talk back.
That's right. It's just big eyes,
Totally. So. You have developed a very interesting application that's monadic through and through.
Yeah.
And you're going to take us through what you've done and make sure that, like a monad, our understanding is carried through.
Yeah, absolutely.
Until you get to the end.
Yeah, absolutely. So what I was hoping to do essentially was to motivate things last time. That's why I kind of began with what I thought was the carrot. Okay. But I think we have to begin a little smaller.
Yes.
So first I'm just going to introduce the idea of a monad from the point of view of people who are, working on a daily basis making web applications.
Cool.
Right. So that's where we're going to get started.
Excellent. Well, let's get started.
All right, cool.
Great. Thanks for coming. I will ask questions probably from behind the camera.
Oh, okay, cool. Awesome. Okay, so I like to always carry a map in my head. So this is the kind of map that I have for this series of videos, and essentially what the map is of a standard application, right? You got some user clicking on a browser which issues this requests through the cloud, right? So you have some kind of request stream. You have an HTTP parser. You have ultimately that turns into parsing requests at the application level. You got some kind of domain model which touches on a navigation model and a storage model and a query model, right? So essentially a request is kind of flowing through here down to the backstore and then causing stuff to come back. So that's what I want to talk about in the large. That's the big picture. But before we can do all that, I need to introduce some tools. So that's what really this session is all about. Now, there's this joke in the Haskell world that Haskell made this big mistake of calling them monads instead of warm fuzzy things, and I kind of want to say that there's a little bit of some consequences to calling them warm fuzzy things. I mean, look at the bones, right? Oh wow, we did not get the flaming build here. That's too bad. So let's get started in terms of another way of thinking about monads. I like to think of them as kind of shapely monads. Did you dress her up like this? So there's kind of 3 key ingredients in a monad if you're going to use them on a daily basis. There's the notion of a shape, wrapping stuff up in a shape, and then rolling nested wrappers up into a kind of one wrapper. That's the key idea. It turns out that we can embrace shape in a canonical way. There's one idea that's actually underlying all of this, and it's really familiar to most web programmers. Okay, so the idea is you think of the shape, or you think of monads as colored braces. So I put colors in inverted commas because we sort of know what colored braces are. They're really XML tags, right? And the different kinds of tags are really the colors of the braces. And then when you wrap things up, you put them between the braces. And when you roll, if you've got nested tags, you're flattening them out. So shape, wrap, and roll. That's the idea. Now let's look at a little example. right? So again, just all I'm doing is putting some flesh to those words. So we have the tag red, whatever that means. Then we wrap up queen, so that's the red queen. And then let's say we wrapped up knight, and we wrapped up queen, so we have the red knight and the red queen, and we made that whole thing red. Then when we roll it, we just get red of knight and queen. Very simple. It's actually not that scary. Okay? Now, you're going to say, yeah, what good is that to me? Why do I care?
I'm into Monty Python.
Do you really sell cheese here? The crucial point is that virtually any data structure you're going to encounter in like real programming can ultimately be described this way. And sometimes it's even useful to think about describing the data structures this way. Man, I got to say, it is just crazy knowing where to look with all these cameras. So
you just look at me. I'm listening to you.
Cool. Yeah,
You can look at all, and you look at all the cameras and talk to all the 90s out there if you want.
Yo, dude. All right. So I just redid the same structure we saw before, where we now think about the tag set as meaning what it intuitively might mean. We make a set of whatever's of junk in between the tags. So a set that contains the element queen, a set that contains a set which contains knight, and a set which and also the set queen. And when we flatten that out, we roll it up, we have a set that contains the knight and the queen. And you know what? The same thing can be done with lists, right? So, and in fact, the real moral of the story, in some sense, is that somehow list and set are the same, right? I mean, because at the level of syntax, we're not seeing a lot of difference here, right? I mean, they're literally the same. I mean, you get that, right?
Yes.
Cool. All right. So, and they're the same up to one point, and that point is a pair of equations. We can write them down exactly, right? So the first equation says A plus B is equal to B plus A. So there's some kind of commutativity going on here. And there's also, if you add an A to an A, you get back an A. So this is sometimes known as idempotency. So commutativity and idempotency are true of set and not true of list. So how am I going to relate this to shape, wrap, and roll? Right? Where does this plus come from? Right? And what's the notion of equality? And why is it related to the shape, wrap, and roll? Okay, so what I'm going to do is I'm going to show you a syntactic transformation which is going to relate these equations here to the shape, wrap, and roll stuff. All right, so and honestly, this syntax modification is how I bootstrap my own understanding of monads. Okay, so if you look here, this is the infix way of writing addition or some kind of combination or composition operator. Okay, and that syntactically could just as easily be written like this in prefix style, right? So we know that this is just massaging syntax. We haven't changed any semantics. And for all the XML wonks out there, right, we know that this is just another way of writing that, right? Or this is a perfectly reasonable way to represent that information, right? We just add enough angle brackets to make it dangerous. And then now we introduce the shape, wrap, and roll stuff. Okay, because we're going to say that this is the same as that. Well, let's check that out. Is that really true? Well, the way to see that this is the same as that is suppose I take A and I nest it inside plus angle brackets. Well, there it is, right there. And I take B and I nest it inside plus angle brackets. And then I nest that whole thing, that pair of nestings, inside angle brackets. We know that if I roll, that will roll up and get rid of these inner ones, which will get me back to here. So this and this are the same. Is that making sense? Okay, cool. So then if I write it in terms of our operations, what we do is we wrap A, that's nesting it in the angle brackets. We wrap B, We put that inside the angle brackets. We roll it up. Okay? So now let's just look. Look at that. There's our plus. Okay? Because that plus turns into that plus. So let's just look at this little expression in the yellow. Okay? In the case of both the data structures list and set, what we're really seeing is that as long as we've safely wrapped A inside a list or a set, then the plus is just the natural notion of plus inside that container. Okay? So in set, what is that? Well, it's just union. Right? That's all it is. I take two sets and I just put all the elements together. There it is. And in list, it's append. And we know that append and union are not the same. So in particular, looks like it's a fair trial here. We take set and we union it with set 1 and we union it with set 2. That's the same as if we took set 2 and union it with set 1. So that was exactly, let's go back. That was exactly that guy. Okay? And if we take set 1 and we union it with itself, we get back set 1. All right? And that was exactly our idempotency equation. That guy. Yep. Okay? So, now here's the cool thing. Oops. Whoa. Yeah, I went way too far. We can see that clearly these are not true of lists. Right? If I take two lists and I append them, like the list containing A and the list containing B, and I append them, that's not the same as the list containing B followed by the list of containing A. And moreover, if we take a list and we append it to itself, we get a list that's twice as long. Yeah. Right? So this is definitely not true of lists. Okay, so what monads do is they refactor container code. That's what it's really all about, at least at this level. There's more stuff about control that we'll get into. But the key idea is that you can take your container code and you can factor into some stuff that's the same for lists and sets and all kinds of other things, and some stuff that's different, right? And why is that cool? Because that's where you get reuse. That's where you shrink down your code, right? And you make your code more maintainable and more understandable. Okay? So that's essentially all we've said, is that we factor code for list and code for set in terms of two pieces. One is this shape, wrap, and roll stuff. And the other is some equations. What equations? Well, again, equations like these, okay, which are going to be true of some containers and not of others. Now, what's really interesting, and there's a deep reason I point this out, is that lists have no additional equations. The equations, the set of more things that are the same when you do the operations is empty. That's gone. And when you have no additional equations, those structures are called free. Okay? So the free structures are absolutely critical. And the reason it's, this is magic stuff, and I want to get you guys excited. It's kind of hard to get you guys excited right now, but there'll be lots of examples. But the crucial point is that for your whole zoo of containers, they always factor down into the free things together with additional constraints or equations. Now, so what that means is, it's like yesterday, I was at my violin lesson with my daughter, and the teacher was showing her the D major scale. And I said, wait, stop. You don't have to remember the G major scale and the D major scale and the F major scale. There's one major scale. If you remember it like this, whole step, half step, whole step, half step. And that pattern factors through all the scales. So you don't have to remember ton of scales. You don't have to remember 7 major scales. You remember 1 scale. That's what's going on here. We remember 1 scale. Okay?
Excellent.
Cool. So, now, as a part of that refactoring, what we can show is that, or what we can begin to intuit, is that every monad can be seen as a version of a data structure that has a plus and a unit for the plus. Okay? And what we did when we talked about these shapely monads, these monads using this brace metaphor, was to show that there's one metaphor you can keep in your mind to keep all this straight. Okay? And so that metaphor of colored braces, allows you to extend the plus operation over things that you put inside your monad. So now we're really talking about monads as containers. We've kind of shifted to this idea of a monad is a kind of container which you can put stuff into. That's the wrap operation, right? And yet somehow it also has this notion of plus. The container has a kind of combiner which combines containers, and this brace idea gives you a unique representation or a unique way of thinking about extending the plus over the things that you put inside the container. All right. Now it also gives you the notion of unit. Now that's when you know that your metaphor has some power. If you can kind of cover the whole surface area of the idea and it sort of makes sense, coherent sense all the way through. So again, the idea, what I'm trying to get across, at least with this thing, is that you only need one model in your mind, which is colored braces. And as long as you're manipulating colored braces in your mind, you have a handle on the notion of monads. And we all do that all the time if we're programming the web, because we're all manipulating XML. Okay, so let me show you what I mean. So the unit of the plus has a canonical representation as the empty braces. So open tag, close it immediately with nothing in between. Okay? And to see that it's really the unit for the plus, here I've written out a little sample or an example. So if I take the queen and make it red, and then I add it to the empty, right? And then I roll that up, I just get the red queen. And that's the same as if I did it in the other direction. So I put empty on the left-hand side here, I put empty on the right-hand side here. So this really is under a roll. We're on a roll now. It really is an identity for the adding of the red operation, the red plus. So what's really going on is we're generalizing this kind of structure, which is one of the simplest ways of thinking about how to combine things, to this kind of structure. Now, I'm not going to explain what this code means, but I just want to kind of plant some seeds in your mind, right? And just, I'm gonna just keep brainwashing you with this notation until it starts to seep into your unconscious, and eventually it starts to make sense. And part of the reason is because expressing data structures as grammars is extremely powerful. That's essentially what's going on here. I am subtly insinuating an isomorphism between types and grammars. They are the same idea. And what we've really done is we've gone from a non-polymorphic type to a type that is polymorphic. That's the transition from monoid to monad. And the polymorphism is the trick of putting things inside the container. That's it. Okay. So just to summarize then, So the key value of writing your container code, whether it's list, set, tree, graph, in terms of an interface called monad, is that they all share some underlying code, which you get to factor out and maintain one time instead of dozens of places all throughout your code, right? And some additional constraints that make them specific, like set over list. Now, it's really interesting, right? Because it's, to me, I find this super exciting. Notice that, in some sense, list has more fine-grained memory of the operations, right? You know, you can kind of recover the history of stuff you've put in, right? Set forgets a bunch of stuff, right? And what is that forgetting? That's the equations. The equations, by equating things, is a style of forgetting. So that's another way of, that forgetting is a way of remembering the value of monads in the container setting. So is that kind of resonating for you?
It is. It's great.
Awesome. So we go from that idea to, you know, there's a little bit more to the story, and that's that monads actually have to obey some laws. So when I do the shape, wrap, and roll, there are some requirements on the things that I'm calling shape, the operations that I'm calling shape or wrap or roll. Is this a little darker? It looks like, I don't know. Anyway, and the three requirements actually come in three levels of specificity. Now, if you have seen, how are we doing time-wise?
Great.
Okay. If you've seen maybe a Haskell presentation of monads or an F-sharp implementation of monads, then you've probably heard about the monad laws. And when they talk about the monad laws, at least in that computer science setting, they often forget that there's a factoring of the laws. That they happen at different levels. So functoriality is happening at the level of shape. Naturality is happening at the level of wrap and roll. And coherence is happening at the interaction between wrap and roll. Now, the reason I identify those is because it actually talks about a holy grail in computer science. There actually is a holy grail in computer science, and there are whole languages that have been devoted to this. Like Eiffel, for example, was Bertrand Meyer, I think. Yeah. So Bertrand Meyer had this whole idea of building a language to support design by contract. But the problem was that contract was such a big and amorphous idea that it became really hard to find a good wrapper around it. It turns out that category theory, as a basis for thinking about computing, has over the last 50, 60, 70 years, I don't know, let's see, 1950s to about now, 60 or so years, has tested out as a pragmatic approach, just looking at these three things to reason about interfaces. These three kinds of constraints on interfaces, and they've worked surprisingly well. There's this whole zoo of constraints or conditions you might put on a contract, but it turns out that these are enough to cover the vast majority of things you're going to encounter in web programming. So let me again try to reduce this a little bit to something that's starting to look like code. Maybe you're not familiar with code expressed this way, but it's kind of in the ballpark here. We know that if this is really going to be a sensible addition, and that's going to be a sensible identity for addition, that if I add 0 to anything, either on the right or on the left, it should be the thing we had before. And again, if this is going to be a sensible notion of addition, the order of doing the addition shouldn't matter. Okay? Now, the question we have, and this is going to be true of any data structure like this. Okay, so integers work like this under addition, right? Floating point, double work like this under addition. Surprisingly, string concatenation with the empty string as the identity work like this, right? Well, you have to be a little bit careful about, there's no commutativity, but certainly it's associative. So the question is, when we move from this data structure here, which is not polymorphic in A, what happens to these guys over here? So this is a clear pattern from here to here. What happens over in this corner? Okay. So the first idea is functoriality. So let's say I've got some XML data, okay? And I have a function that operates on the XML data, producing some more XML data. And then I have another function, G, which operates on that, producing more XML data. Well, I could certainly, if I have a monad red, I can just put that data inside the monad, inside the container. All right, cool. Now, what would be interesting is if there was a way to think about this monad as operating on functions. Okay, so I apply the monad to the function, and then I apply it to the data. And I apply the monad to this other function, and then I apply that to the result of this. And functoriality, one of the two conditions, says that, that these two things have to be the same if we can make this precise. Now I am going to assume that the general audience here is someone that has at least some sense of what map is. Right? So maybe you're not the world's most monstrous functional programmer, but you probably have some sense of what map is. So this equality actually makes perfect sense if this is just another notation for mapping F over the contents. Okay? So if I write this just to mean whatever's inside the braces, go and run it pointwise over each one. And likewise here, whatever's in between the braces, go and run G on that. Then what we're requiring is, if I, let's say I take the XML out, then now we have expressions exactly in functions. So we're saying that if I have the red on the G composed with F, it's the same as the red on the F, the red on the G composed with the red on the F. So that's the idea for functoriality. There's another condition about identities, but I'm just going to gloss over that. I just want to give you a little sense, a little taste of what this might mean. Okay, naturality is even more interesting. I couldn't find a Monty Python that had to do with unnatural acts, so I'm lying. just couldn't show them on Channel 9. So naturality is a very interesting idea. The idea is that we actually have a whole family of morphisms, functions, whatever you want to call them, arrows, which will get you, which transform other functions. Okay, so let's think about how this will work. Suppose I've got some XML here, and I've got some XML here. Oh boy, I can really got you excited. And I've got some XML transform which takes an A to a B. Yeah. Okay, then what I need is, for naturality of the wrap idea. So actually what we require is naturality both of wrap and roll, but I'm just going to talk about naturality of wrap. I need an arrow which is going to get me from A to red A, and an arrow, which is going to get me from B to red B. And I also need the red F, okay? And it's got to be the case that if I take A and make it red, and now since I've got, a red A, I can apply a red F to it. That'll get me to a red B. So if I run around this way, it's the same as if first I took my A element, or my A content, I turned it into my B content using my F transform, and then I made that red, okay, by using this arm, this one of the family of arrows that comes for making things red. So going either direction has got to be the same. Okay? Now coherence has to do with the interaction between wrap and roll. Now the way to think about this is this is just an instance of our associativity equation. Let's remind ourselves so we keep a simple pattern in our heads. So here's associativity. Well, all it says is if you do the plus first between these two and then between the result of that and that one, it's the same as if you do the plus first between these two and then between the result of that one and that one. So here, essentially we've expressed the same idea. So suppose I make a red A and a red B, and then I, sum them up, right? And I make my red C, and I sum them up. Okay? Almost there. The big cane is about to pull me off the stage here. It's got to be the same as if I did it in the other direction. That's essentially a statement of a coherence condition.
So I have a question.
Yeah.
When you said you did sums and quotes, could what you mean there be compose?
Yes.
Okay.
That is exactly the idea. So let me leave you with one final thought about this holy grail of design by contracts. And I want to say that of course, it's a good idea. So just as monads factor containers into shape, wrap, and roll, plus some equations, contracts do not have to support all manner of rely guarantee predicates. And you can think of that as essentially, for those in the know, you can think of that as essentially the downfall of Eiffel and one of the problems with a general Ushionov assertion. If you could winnow down what you had to support to just functoriality, naturality, and coherence on your interface as the data you add to interfaces to turn them into contracts, life becomes much more feasible. Anyway, so that's where I'm going to leave it for today, and we'll pick it up again next time to show how this all begins to fit into running code.